Okay, I just wanted to say one last thing about this previous problem from the previous video. You could use a supernode. So you have I1 and I3 just like before. I2 can go around here. You just have this extra voltage you got to take care of. So I1 minus I2 is going to equal the current source here. And then the loop. Let's see, what loop is this? Yeah, 1, 2, and 3 are involved in the middle loop. Here's that voltage. Here's the voltage source in the middle loop, and then mesh 3 should be what we saw before. Okay, no, not quite, because now we have I2 going on. We didn't have I2 before, so a little different equations. But when we sort all the things out, we should get the same answer. There we go. Source superposition. Now the deal there is that you can cross out one of the sources and say, this is zero current, and solve it for when there's only one source, say this source. You find that solution, and then you go on, and so you find the solution this way. Then you add it to the solution when you presume this is the only source, and that the voltage, you're crossing out the voltage source, and you only have the current. It makes voltage sources in the zero voltage means there's no current. Or excuse me, as much current as you want. I shouldn't say that. Zero voltage means a short. Zero current means an open. Okay, and then you go about superimposing the solutions. Total IL equals solution number 1 plus solution number 2. That's because of linearity. Total IL is the sum of these two. Total VL, same thing. Because of linearity, the solutions are linear in this, and they're linear in I sub s, so we can solve it separately and add them together. Okay. Is taking a complex circuit and breaking it down into two easier circuits. That's all it's doing. That's what superposition is all about. Okay. So you can, here's an example doing it, and I won't go through that. I'm going to skip this one. Or should I say, I'll go through it quickly. It's on your handouts, but by going through it quickly, at least you can see it here. You don't have to go to the handouts. I'll go kind of slow. Use the pause button on your videos to work through this, to figure this one out. I gave you the basic outline of how to go about this problem. And we've done DC problems like this before. And here's Thevenin's again. We're coming back to Thevenin's equivalence. Okay. You replace the resistances with impedances of source impedance. And of course this becomes an AC current source, and this becomes a alternating current voltage source. And this guy got flipped around. Take a look at this. ZV. I'm going to have to fix this slide. Oops. There we go. Eraser. I'm flipping it around. You guys could do it yourself, but what the heck. Equals Z. And VS equals Z IS. Okay. Thevenins and Nortons again. Source transformation. This just does that. You can replace, I'm going to outline it again. I'm not going to actually do it. Say you can replace this with a Thevenin's equivalent, and you can replace this with a Thevenin's equivalent, and you can convert a current source to a voltage source, so you have a couple voltage sources and resistors. Or maybe it'd be better to have a couple of current sources that are hooked together. You'll notice a couple of current sources and resistors. So let's see the general approach. Oh, they go to the voltage sources. Okay. And they convert the current source to voltage sources. And then transform it to currents. There we go. So this is using Thevenin's and Norton's to go to do your source transformations. Change your source into something different. And the end result, which is the same as what we had before, as you'll notice. So just substituting this for whatever this was. Everything is, and this is a reminder, we're talking complex numbers now. AC, it's virtually identical to DC, except you're dealing with complex numbers. Okay. This is the load current. You just take it out and you figure out Thevenin's equivalent circuit for everything else. Is this a lot easier? It looks like they've done a source substitution too, changing this into this. Like I said, I'm just going to outline it. I'm not going to go through it in detail. You can do that on your own. Same idea. Sometimes you need to go back and forth. Norton's wouldn't be too bad. So get the equivalent impedance and what is the impedance of the network that this sees? And remember that you can make the voltage sources into shorts and the current sources into opens. I need a little to drink right now. I personally like Norton's and Thevenin's, by the way. Now that we've got the Thevenin's equivalent impedance, now we need to change the sources into current sources. And we can find I naught from there. Okay, again, it's just putting everything together. Notice we have a dependent source over here. So we can't use superposition because that only applies to linear circuits. This is nonlinear. This makes it nonlinear. So you got to use nodes, loops, Thevenin, Norton's theorem. And the standard techniques that we know how to do. Let's see, there's one part. There we go. An equation, this defining equation for this right there. So we'd make the substitution. It's just algebra, literally. Okay. Big, complex, break it down into smaller pieces and figure it out. And again, lots of examples that are just very complex. I'm going through them, just zooming through them. The only difference between these and simple examples is you're taking these complex ones and breaking them down to simple. You're making them simpler, lots of little simple ones, instead of one big complex problem. Go back to your DC. Go back to your studies about DC circuits and use the same ideas. You just got extra complex numbers. Use a tool like New Octave or MATLAB. Okay. Let's see. There we go. And we're noticing this shows the equivalence of all the different techniques that you used. Okay. This is back to that one problem that we did a while back that we went into detail about. Is it the same problem? Okay. So I'm just scanning through. You can pause it to take a little closer look. And of course you can grab the handout and use the handout instead of the video. Just a whole bunch of problems. You can see the sequence. One thing about a video though, you can see the sequence. So you can have the handout in front of you and watch the video to see how things sequences through. Now, I'm going to stop here. There's one thing I want to talk about this. We have sources with different frequencies. So we're going to talk about that next. And it should be really short, as a matter of fact.